Hi viewers, in this video I am going to explain what is F is equal to ma. So you all know this famous equation which is the Newton's second law of motion, but the question is how many of you know this equation in a practical way? What it actually means? Do you see this equation around you? Is it everywhere? When a bird flutters, do you see this equation? Or when somebody hits you and you fall to the ground, and is there F is equal to ma there? So what does it mean in a practical sense? So I'm going to make you understand this equation F is equal to ma through a couple of simple experiments, and at last I'm going to show you that this F is equal to ma has a comparison in rotational motions and in electrical circuits. Viewers, welcome to Marty Z. I am Martin Chirangal and I am a PhD research scholar in IIT Delhi. The videos in this channel are for educational purpose, where I would explain the physical and the mathematical concepts in a more practical way. According to me, to understand concepts in physics and mathematics, you have got to visualize the concept. You need to understand and visualize it. That is what I will help you in these videos. These videos would be helpful for high school students and engineering graduates who are interested in physics and maths. So talking about the Newton's second law of motion, which is F is equal to ma, let's see these simple experiments. Okay, you have seen the experiments. You would doubt, what this simple experiment would mean, or how can you explain F is equal to ma from these simple experiments. So in order to make you understand what is F is equal to ma in a practical way, I'm going to make you go through a three-step process, where the first process is to observe whatever you saw in the experiment, and second process is graphically representing whatever you observed from the experiment, and the third process is how to represent the whole graphical representation into a formula. So as you see the video, you will understand the whole process. Okay, in the first process, what are all the observations? So what did you observe? So I can say initially the can was at rest and it was not moving, and at time t1 I gave a force. It's a small interval, say from time t1 to t2, I'm giving a force, okay? And due to that force, the can started moving, right? So the effect is movement, which can be represented as velocity. And when I took the force from time t2, it slowly rolled and it came to a halt. So we can say that the velocity kept on decreasing and it came to a zero. It came to a halt. So these are things that we observed, right? Yeah. So what is the second process? Second process is graphically representing whatever that we have observed before. So what are you going to represent in a graph? That's a good question, right? Yeah. Okay, so we are going to represent the input function, which is force, and then the output function, which is velocity. So in a graph, you always have an x-axis and you have a y-axis. So initially, you're going to draw an input function force. So you know that till time t1, there is no force, so the force is zero. And for a small interval t1 to t2, you are giving a force. And at t2, you are taking your hand out, so the force is going to zero. So this is the input function force in time axis. Next, we are going to represent the output function, which is the velocity in time axis. Yeah. as you observed, till time t1 it is not moving, right? So the velocity is 0. And from time t1 to t2 it started moving. So the velocity is increasing from 0. And when you took the force at time t2, and from there, the velocity kept on decreasing and it came to a halt. So we know that the velocity is decreasing from time t2 and came to a halt at time t3. So that's how you can represent the input function force and the output function velocity with respect to time as a graphical representation. So we'll go to the third process, which is nothing but a formula which explains these graphical representation or the observation. So what is a formula that represents the previous graphical representation? Yes, it's the same equation, F is equal to ma. But the question again is, how F is equal to ma is explaining the previous graphical representation or the observation. So what I'm going to do is, in the blackboard, I'm going to derive a small derivation which will make you understand that F is equal to ma is nothing but the observation that you made or the graphical representation of the input and output that you made. Yeah, let's see the derivation. Yeah. Okay, let's see the derivation. F is equal to ma. In this, F is nothing but forces on the object, and m is mass of the object, and a is acceleration of the object. So I can also write acceleration as dv by dt, which is nothing but the first derivative of velocity with respect to time. I'm doing a small substitution. And what I'm going to do is, I'm going to integrate on both sides. Integration and differentiation are inverse functions. Just like addition and subtraction and multiplication and division, integration and differentiation are inverse functions. So if I integrate this, what we get is velocity in this experiment. M is nothing but the mass of that can. This mass of the can remains constant throughout the experiment. It doesn't change. So what I can do is I can take the m out of this integration. I can do one thing, I can simplify this more. I'll assume that the mass of the can is 1 kg. Now this equation becomes from F is equal to ma, we have derived and we have come to this formula where velocity is nothing but the integration of force for some time dt. So we know that F, force is the input here, and due to that the can started moving, and that is the velocity. Output velocity is nothing but integration of the input for some time dt. Viewers, regarding this integration and this differentiation, in future I'll take a video what this integration and differentiation actually means. If you see that video, you'll be able to understand practically what is integration and differentiation. So now the input can be of any type, and according to that the output varies. So in that integration and differentiation video, I would have explained about this various condition of input and how the output is going to be. Anyway, I'll give a small summary here, and let's see. What I have explained here is, this is the integration, so this is the input and this is the output. So what this means is that if our input is something like this, which is a positive constant value for some time, the integration of that is nothing but a positive ramp, and it will remain at that value till infinity. So we'll take another type of input where it is a negative constant value for some time, then the integration of that will be something like this. It will be a negative ramp and it will remain at that value till infinity. You have got a relation between f is equal to ma and an equation like this, where output is nothing but the integration of input for some time dt. If the force is any of these forms, then you will know what the velocity, then it will be like this. And now we'll go to the slides. Okay viewers, you saw the derivation and you saw how you got v is equal to integration of force for some time dt from f is equal to ma, and you saw the summary of how the output after integration varies according to the input. Okay, let's go to the graphical representation of the experiment that we did earlier. If you go to the graphical representation and you compare that with the summary, in summary we have told that if the input is a positive constant value for some time, the output is going to be a positive ramp and it is going to stay there for time infinity. But if you see the graphical representation that we did, we saw that the velocity went to 0 at time t3. So the question is, are we missing something here? What are we missing? Is there anything missing in the input side? So if you go back to the input function, which is force with respect to time, the question is, the force that I gave, is it the only force that's acting on the can? So are there any other forces? How about frictional force? The moment you took your hand, the velocity came to 0 due to this frictional force. So this frictional force actually opposed the movement of this can. So it's actually the opposite to the force that I applied. Now we'll try to draw the whole input and the output. So from time 0 to t1, there is no force, there is no velocity. From time t1 to t2, I gave a force. So it is a positive ramp, which means the change in velocity with respect to time is positive. So it is increasing, the velocity is increasing. At time t2, I took my hand and the velocity kept on decreasing due to the frictional force, which means the change in velocity with respect to time is negative. dv by dt is equal to negative. And at time t3, the velocity came to a halt. And after t3, there is no force, there is no movement. So the dv by dt, the change in velocity with respect to time, is 0 again. Just think, what if we had done this experiment in space? In space, there is no disturbance force as this friction. At time 0 to t1, there is no force. At time t1 to t2, we are giving a force. The can is moving, the velocity is increasing. And the moment you take your hand, it remains at that particular velocity for time infinity. You know, it sounds strange, but that's the reality. The velocity that it has acquired at time t2, it will remain till infinity, because there is no other force to stop it or to accelerate it in space. From time t2, the velocity is constant, which means the change in velocity with respect to time again is 0. You know, there is some velocity, but there is no change in velocity, so dv by dt is 0. So we'll come to a conclusion. What does this f is equal to ma tells you? So if there is an object, and if that object changes its velocity, then a force has acted on it. So let's take an object. If that object changes its velocity, say if it is positive, which means it is accelerating, then a force has acted on it. Or if you can take the object as decelerating, which means dv by dt is negative, then also a force has acted on it. So this is the conclusion. So if any object, if there is a change in velocity, it means a force has already acted on it. In part 2, I'll explain an experiment with vertical motion, and I'll explain what is momentum, which is nothing but p, where p is equal to m into v. And in the start, I have told you that f is equal to ma has a comparison in other domains like in rotational motion or in electrical circuits. So this f is equal to m dv by dt is nothing but t is equal to j d omega by dt in rotational motion, and v is equal to L di by dt in electrical circuits. I came up with this V is equal to L di by dt while doing this video, that F is equal to M dV by dt is similar to V is equal to L di by dt. Inertia instead of M, it is inductance L here, and the equivalent friction force here is resistance in electrical circuit, Ri. Electrical enthusiast, you can think about this. Thank you viewers for seeing this video, and bye until we see the next video. See you.